Let me solve one more problem on a tapering section. A 1.5 meter long steel bar is having a uniform diameter 40 millimeter for a length of 1 meter. In the next 0.5 meter, its diameter gradually reduces from 40 mm to 20 mm as shown in the figure. Determine the elongation of the bar when subjected to an axial tensile load of 160 kilonewton. So it is given that Young's modulus is 200 giganewton per meter square. So this is the question. So this will be the figure. See here, if you observe this figure, so there are two sections. So this is your section 1 and this is your section 2. So this section is having uniform cross section. Uniform cross section with the diameter 40 millimeter. Whereas this second section, here the cross section, it is varying. So uniformly varying cross section. So here the diameter is, bigger diameter is 40 millimeter, whereas smaller diameter is 20 millimeter. So here total elongation delta L equals delta L1 plus delta L2. So delta L1 is elongation of section 1, whereas delta L2 is elongation of second section. So let me list the given data. First, for section 1, length will be 1000 millimeter and axial load will be 160 kilonewton. So which is equal to 160 into 10 raised to 3 Newton. Whereas Young's modulus, so it will be 200 giganewton per meter square, which is equivalent to 200 into 10 raised to 3 Newton per millimeter square. Okay, so this is for section 1 and diameter of the section 1 will be 40 millimeter. So it is uniform. So first let me calculate delta L1. As the section 1 is uniform section, so elongation can be calculated by PL divided by AE. So here P is 160 into 10 raised to 3 and length of section 1 will be 1000 divided by area. So you know the diameter, so your area will be pi into 40 square divided by 4, pi d square by 4. So area will be pi into 40 square divided by 4. So this is the area. So Young's modulus, so it will be 200 into 10 raised to 3. So if you simplify this equation, you will get delta L1 as 0.6366 millimeter. So this is elongation for first section. So let me write somewhere here delta L1 equals 0.6366 millimeters. Next, in the next step, so let me calculate the delta L2. Delta L2. So if you observe the figure, delta L2 will be uniformly tapering circular section. So this is uniformly tapering circular section, for which elongation will be calculated by, so 4PL divided by pi e, so 1 divided by d1 d2. So let me substitute. So delta L2 equals, so 4 into P 160 into 10 raised to 3 length. So length of second section will be 500. 500 divided by pi into Young's modulus. So it is 200 into 10 raised to 3. So 1 divided by d1, bigger diameter, it will be 40. 40 multiplied by d2. So smaller diameter, it is 20. So if you simplify this equation, so delta L2 equals, so it will be 0.6366 millimeter. So this is the elongation for second section. So let me write it here. So delta L2 equals 0.6366 millimeters. So once you know the elongation for section 1 and section 2, so it is easy to calculate the total elongation. So delta L equals delta L1 plus delta L2. So delta L equals, so your delta L1 will be 0.6366 plus delta L2, it is 0.6366. So final or total elongation, so it will be, so final elongation will be 1.2732 millimeters. So this is the elongation for this given section.